My name is Nando. Very happy to be here today. I've been asked to talk today about some folding engines and models, and actually I was pretty motivated to talk about certain topics I stumbled upon while working on the engines for the Flash applet in the game. So I want to start with a warning. Certainly, for me, it is about doubting everything. It's twofold. It's as well very good advice when you are dealing with science, I feel, personally. And as well, I am not a scientist, so maybe you should take whatever I'm going to say with a grain of salt. So fair warning here. I will start with talking about RNA folding models and a little bit the history of them, with the first attempts at coding and predicting secondary structure was done in the 70s. And later on, actually that's a very good question. I didn't do a very good research on this. I have no idea what those algorithms were at the time in the 70s and what was the principles behind the secondary structure derived by Eternacon. But Nusinov with the best pair maximization is a pretty simple scheme where it simply tries to maximize the number of base pairs that you can build with a specific sequence. Later on in 1981, Zucker came up with a much more evolved model based on free energy minimization, and this is the model that we know today as the nearest neighbor model. At the time, it was only about minimum free energy structures, the MFE, as you all know. Later on, in the 90s, the Tim McCaskill developed this into a full-fledged partition function and full thermodynamics picture of the ensemble of structures in RNA. So about the nearest neighbor model, I think everyone here is probably, I'm going to do this very quickly. It's very, very simple in the sense that we're considering the areas surrounded by the base pairs and the backbones. You can define single units to which you can attribute or assign a certain free energy contribution. Those are the kcals that we see in the game. And each of them have different parameters. And yeah, we're going to see this a little later now. In Eterna, we have been using historically, at the beginning, the first engines were Vienna version 1, and the parameter sets that were delivered with them are named Turner 1999. Later on, there was a big part of my work actually in the project. We integrated Vienna 2 engine, and this time we have the Turner 2004 model as the default, but there are possibilities to use some other models, some alternatives. We talked about this a little earlier. The Andronescu 2007, I tested it a little bit. And late addition, I mean, it was not so long ago that we added the ability to compute oligo combinations through NUPAC in this version. One of the drawbacks of NUPAC is that by default it uses a parameter set from 1995. I refrain to give a name here because I had a conversation once with Cody Giri, maybe some of you know. I was saying, I read somewhere this was from Sarah, the team Sarah, and he was saying it was something else, Matthews or something. So I'm not too sure who produced actually the 1995 parameters. And we have also as option the Turner 1999, but with a little drawback, which is actually a mystery to me. One of them I couldn't solve yet is that Turner 1999 doesn't come with enthalpy parameters, which are essentially something that helps you to calculate melting points or to evaluate variations according to temperature. And those do not exist in Turner 1999, and that's why in NUPAC you don't have them, but somehow in Vienna they do have enthalpy parameters. I don't know where they come from. Kind of strange. Essentially, what I wanted to talk about today is a special and very interesting case. I mean, at least a shocking case to me. Here, more specifically, it's a design. I don't know if you guys recognize it. This is the Exclusion 3 puzzle. I'm not too sure which round it was, but this was a design that was tested, and actually a contribution by Salish99, Lars. And I want to go through actually the predictions of each of our engines on this specific sequence. Specifically here we have Vienna that is telling us that this multiloop here is practically stable at minus 0.1 kcal. For anyone who has been working in the labs for a certain amount of time, there's something of an eyebrow raiser. Really, what? This is stable? Those danglings, bases are going to be stable? That's kind of weird. And that was, even at the time when we were doing it was years ago, it was known that the evaluation of junctions, multiloop branches, were really somehow faulty in the Vienna engine. That's why it's no surprise to see that in Vienna 2, the same multiloop is evaluated at plus 2.3 kcals. Still, this is probably underestimated as an instability, because NUPAC tells us this should be a plus 5.6 kcal instability for this same multiloop. And there is the strong difference. The Vienna engines tell us that this switch is not going to work. But if this multiloop is really that unstable, NUPAC predicts this switch is going to work. Now, who is right and why? The lab, sorry? Those are the Turner 2004. Turner 2004. In theory, it should be Turner 2004, and that's what prompted my own doubts, because I thought that is strange, and I went looking for the answer actually. So there is a website. This is all public information, and you just need to do a little bit of digging to find that in the nearest neighbor database. So here we have the details of how the Turner 2004 computes. I'm not going to go too much into the details of the mathematics and anything, but this is fairly simple. I'm going to ignore the stacking, whether we have some mismatch-mediated stacking, coaxial stacking and stuff, etc. We are just looking at the delta G of the initiation. And essentially there are 4 parameters. 3 are really important. They are named here A, B, and C, and they are related to different things. A is a constant. It's basically the how would I call it? The base instability of a multi-branch loop. And then you have correction factors, which are an average asymmetry. Average asymmetry I can show you here. Essentially, what it means is you look at a stack, a helix, and then you compare the lengths of the unpaired segments around that stack. So here we have a difference of 1 to 12, which is a difference of 11. That's the asymmetry for this branch. The asymmetry for this branch is going to be also an 11, and the asymmetry for this branch is going to be 1, 1. It's a 0. And that's the average of that is, in this case, 7 something, because it's 11 plus 11, 22, divided by 3. So that's what is the average asymmetry. It's explained here much better. But there is a factor. There is a ceiling. Everything that is over 2.0 is just considered to be a 2.0. And finally, there is a last parameter about the number of branching helices. Those are usually stabilizing factors. So, in practice, I wanted to compare what is to be found in the Turner 2004 published parameters, which are in the lower left of the screen, and what the Vienna RNA package team has published. That's what you see on the right. I hope it's going to be visible. But then I compared point to point everything that I found. A note here the values in the lower left are in kcal. The file for the Vienna source code here is in dkcal, which means you want to convert from one to the other, you have to either multiply or divide by 100. So here what we can see is that essentially for the first parameter, A, we have it's pretty close. I mean, the 930 matches very well with the 9.25. The 3000 is within the error margin of this 38.9 actually. So this is pretty close and pretty good. But this value, the C value, which is the stability, if I go back, the C corresponds to the number of branching helices. So here is where we have a certain, and for me, a very important discrepancy. In the Turner parameters, this value is about minus 0.6. And as you can see in the Vienna RNA, minus 90, which corresponds to a minus 0.9. That's a 0.3 kcal difference per branch. So that's certainly a little bit much. And there is also a really very strange to me difference about the enthalpies. As you can see here, it's a minus 2 kcal, and it should be a minus 11, minus 12, and that doesn't fit in the error bar. It is really very strange. And finally, there is the other factor is this parameter B. Well, I looked and looked and looked, and I couldn't find it in the Vienna RNA. So the asymmetry factor doesn't exist in the engine, which actually is not a mystery at all, because this is a completely intentional omission that you can find in the paper published in 2011 when they released the new version of the Vienna RNA package. So they actually removed or refrained from implementing some exceptional contributions. Or they call it highly specialized configuration. Okay, and specifically, one of them was this average asymmetry correction penalty in the multi-branch loops. There is another one which is something a little bit more special. It's about the strain. When you have a 3-branching loop which has just no or just one unpaired base, a very constrained multi-loop, then there is an additional penalty prescribed by Turner 2004, which is not implemented in Vienna RNA. But to me, this is far less important than here, because If you look carefully at this one, we have 3 branches, and if we correct the parameters for the number of branches, we get actually a penalty of 0.9 kcals. The asymmetry of the loop is going to get us an additional 1.8 kcal penalty. So in total, this loop should never be a 2.3, it should be a 5 kcal penalty instability. And that makes all the difference when you consider that in the switch, what we have to play with is precisely in the range of 2-3 kcals. This is going to completely throw off any kind of prediction that you're, or kind of work that you are trying to do when you are trying to play with 2 kcals to switch from a structure to another. So here is the part that is, I would say, yeah, that's more personal, that's my opinion much more than facts. What I presented until now were things that I found out about, and they are pretty documented. I can give you the link to the slides, and you will find also all the links to all the pages, certainly.
How is the energy?
That's an excellent question. I didn't investigate that. Oh, the question asked by Richu is why was the free energy contribution of the multi-loop negative in the Turner 99 parameters? I'm not sure. I didn't investigate the source code of Vienna 1.8 because anyway, this is an engine I wasn't planning on working on, and I thought, okay, I don't know what they included or what they didn't include from the Turner 1999 parameters, and eventually that does match. Yes? So the question is, were every boost applied? I think so.
Yeah, okay.
I think so. So here, what I'm going to say is a little bit more personal. It's my impression of what happened and what is going on here. Essentially, it's about the purpose of a folding engine. Essentially, why did scientists write a prediction tool? And there are certain details in the engine itself that can help us figure this out. The first one is what I call the RRE hack. Here you see at the bottom, maybe, there is a number of specifics. Those are parameters that are meant to be corrections to the general rules. Specifically here, the hexaloops are what they are called. Those are sequences that are very well known because they are the hairpin loops of a specific signal called the iron responsive element in RNA. This is something that you find in the human genome and in mammals and in many animals, and you find this signal in the untranslated region of many, many genes, actually, dozens. And this is all related to the metabolism of the iron, essentially, all those genes. And this signal is very, very important, certainly, but does it justify that we have a very, very specific set of exceptions that is added to the RNA folding engine? Why do we care what this specific signal folds into? By the way, here, this is supposed to be a boost and supposed to give us an hexaloop. The reason why I call it a hack is because this signal, I don't have a 3D model here, but you can find it online. It's actually the C and the G tend to pair, and this tends to form a kind of a tri-loop. But at the same time, this is something that actually connects to an IRP, which is the iron responsive protein, because this is part of a network of regulation, and this down-regulates or up-regulates. I don't remember exactly, but it has a role to play in an interaction. This is an aptamer, actually. It binds to a protein. Why we do have this here, I think the reason for that is the reason how they evaluate the software. How they do this, essentially software, you can evaluate it for two different kind of things. The one is the pure software. It's about its performance, how fast it is, what is storage footprint in terms of memory or hard disk and everything, etc. Those are objective parameters for software, and that's on the side. The other one is the specificity and the sensitivity, as mentioned by Purvis, for instance, to a certain to a certain set of targets, which are the RNA strain database. They tested their software and they judge the quality of their software by testing this. And all of these RNAs are naturally occurring ones. I don't know what you think, guys, but I call it a bias, personally. It is, because all RNAs are not naturally occurring, and specifically the targets or all the sequences that we are constructing in Eterna are not naturally occurring. So I think they tuned their parameters so as to get the best possible score for their data set. The RRE signal presence in the parameters are assigned. The fine-tuning of certain things in the multi-loops as well. You have to notice as well that, like over there, the multi-branched loops are the least populated elements. That's where we have the least information. So they can play around with that, and it's not going to affect their score very much. Everything else is going to. So that's what I wanted to say about the topic, that I found some things that I found personally questionable. One of the things is Vienna RNA decided not to implement those features in their engine, and as far as I know, the latest version doesn't have them either at this point. And this begs the question, what we can do about it. I was asked recently what I was doing with my Vini boat, for instance, in the FMN switches. One of the things I did was to correct for this 90 parameters down to 60. That's why I called all my boat designs, I tagged them as pessimistic. I was trying to be pessimistic about the folding of the multi-loops, pessimistic also about the binding of the FMN aptamer and stuff like that. Those are the little changes that I could actually include in the Vienna UCT boat. The one I couldn't do, because this is dynamic programming at a really deep level, is to add these contributions about asymmetry. And I think if we had some engine, and we've been dreaming about that for a long time now, to have actually our own folding engine, object-oriented, that would be, yeah, it has to be. I mean, seriously, everything else, I've been looking at the code for a long time now, and there are good and terrible at the same time for different reasons. Yes, seriously. So, but this is a huge undertaking, seriously. It's something really, yeah. So, that's what I wanted to talk about. If you have questions.
We just take one of their engines, estimate all the parameters.
So the question by Hadrian was to whether we can reuse an existing engine and actually tune the parameters. So there has been actually efforts in that direction, but as I said, it's a pair of things. If you have the parameters, fine, but if you don't have the code to handle those features, then you can do nothing. So essentially, you have to go very deep into the dynamic programming. For instance, ligand binding was something rather complex. I had implemented my own hack about it, and I was scooped recently by the Vienna team because in their latest version to something, they have actually implemented something like ligand binding, a more generic version of it on top of that. Which makes me annoyed because precisely I spent hours trying to come up with the proper, in terms of thermodynamics and dynamic programming. Okay, I have the proper thing where I can calculate properly the minimum free energy, I can calculate properly the partition function, everything is fine and good. And then the next version comes with it, and that's why I didn't even start working on integrating this asymmetry parameter, because I don't know if in 6 months or a year, the Vienna team is not going to come up and say, hey, we have it now. So the question is, did I contact the Vienna team in Vienna and ask them if they could do something for me? I pondered. I really was hesitating to actually drop there because I'm based in Zurich and the flight to Vienna is about 2 hours. It's really quickly done. And I thought a moment about going there, going up and, hey guys, can you, my problem is I don't have any academic credentials. I show up like that and say, hey guys, can you do something for me? I think I need the backup of some, okay, if I come here with, okay, Stanford University would like, but for that, I need Riju or anyone here to...
Yeah, 2 things to clarify. One is that, I mean, you are an employee of Stanford now, so...
Yes.
But the second thing is that the ligand binding in Eterna was put in there, the first incarnation was put in there by Ji Hyung Lee in 2012. It was well before the Vienna folks were doing anything. I talked to them about this stuff beforehand. I've also been in contact with the new pack developers and so forth. So, it's not like, I mean, I didn't realize that in 2.2.3 they put something in, but we did talk to them before. We did ask. It's not like we're trying to go solo.
Okay. Yeah. Well, the thing is that doesn't solve the other issue that all those engines currently are non-object oriented, and this is pretty wieldy. I mean, you have to imagine the effort to translate that code and to use it in Flash, because this is C source code, and you have to translate it through an abandoned product called Alchemy into a byte code for the Flash platform. I promise you that was really a challenge, and it's kind of a miracle that we have now those 3 engines. I've found by miracle a solution to make those 3 engines work together, and it was not a given. Seriously. It's not talent, it's just chance, seriously. But I managed it. But I don't think this is a solution in the long run. At some point, I think all those engines have to come to something. By the way, Vienna has started to go into providing an API that is object-oriented. And certain primitives have gone actually behind it, which means that essentially now you have a kind of an interface, a wall where you see something rather clean actually. I haven't gone into the details now of their latest release, especially because it's really recent, so it's bound to have quite a few bugs. I would rather wait that they clean up the obvious mess after the release, and then in a couple months, oh, okay, let's look into it. But the appearance is the code looks cleaner, much cleaner than it was. So maybe that would be something interesting for us. But certainly.
Yeah, I think there's just a convergence here, whereas in the past it was the biochemists who had to take all these average measurements of stability, and you guys have so much training data now, and it's accumulated so fast. They may not fully appreciate everything that you've got, right now. I've worked with Dave Matthews before, and he's there with Doug Turner.
Yeah.
And we were talking just about 3 or 4 months ago about he wanted to make an RNA folder that used energies for modified nucleotides. And so anyway, I'm happy to open a channel just so that there isn't sort of duplication of effort, or with this much raw data, I mean, they would be crazy not to want to just exchange and just, I mean, it's asking a lot to coordinate efforts, but at least knowing what's being done and then saying, oh, well, you don't have to do that. We're doing that. I think there's a lot to be gained there.
Yeah, I think that's a great idea. I also talked to Dave actually just 2 weeks ago, and the other nice thing that I bugged him, like, why don't you have object-oriented code? And Dave's the sweetest person in the world, and so he said, oh yeah, I have a branch that is I want to merge maybe later this year. So it's been bugging him too. But the interesting thing about Dave is that he wrote RNA structure. This is the other package. We haven't been using it in the late 90s. And so for him, it was pretty impressive that he wrote it in C as opposed to in Fortran. So I mean, that gives you a sense of these packages. They're really classic packages in structural biology, computational biology, and their roots go way back. And that's partly why it either is going to take a new effort or convincing them to do a major overhaul to bring them into the 21st century.
Yeah.
All right. There's a LP6 has something to say.
Is gone missing? Okay.
Just a second. I pinged him in chat. He's talking to somebody. So.
Yeah, that's.
Okay, LP6, you're losing your opportunity to speak.
He just replied. He's ready to ask the question.
Hello? We're waiting for the question.
He's on chat. He says, "Oops,"
Oops.
and then he says, "Darn."
Okay.
Maybe.
How's that?
That sounds much better.
I had the wrong input turned on. Okay, so I'm kind of adding on to the dreaming a little bit. What would you think about kind of looking at something like kind of a bring your own model approach, where you kind of could create some sort of some platform or generic implementation of what you might call an energy model, where you could come in and kind of develop your own parameters? Because I'm thinking about something like the strategy market. But what if, like, while I'm designing for a lab, on the fly I could say, well, what if this didn't actually work like this? Maybe this multi-loop would be a little bit less stable, and how would that affect my design? And that would kind of allow us to, as players, to have a deeper connection into not just saying, well, here's my hypothesis, now some dev team member go code it into the model, but actually being able to on the fly kind of test things out and see how they react, or comparing it with actual lab results or something like that.
Well, I would say it would be a little optimistic to imagine that you can easily implement something like a plug-in style system into dynamic programming. I will not go into the details of what dynamic programming is here. that would take way too long. But if I can suggest something, you can just download the Vienna RNA package and take a look at the source code. And you will see that there are two phases of computing. One is the filling up of large tables, pretty large, and another one is the backtracking. And all of that is very, very, very delicate. So offering something that allows you to tune, play with certain features, for instance, parameters is not really a trouble. You can tune parameters. We have those files. I've shown them. I mean, it was an excerpt, but the features themselves, like what I was talking about, in the sense that, okay, the asymmetry inside a multi-loop, let's have a penalty for that. Implementing this kind of things, especially dynamically, is a really tough problem. I don't know how to solve that personally. I have no idea. Riju has been.
Well, you just say that.
Yeah. So for the parameters themselves, we can tune them. And there is actually, I'm still late in documentation of the Eterna scripting interface, but there is actually an API that allows you to upload a parameter set to a specific engine. I did that already with Vienna 2. It works. It's simply a matter of documenting the functionality and also documenting all the parameters, more or less, so that you know what you're doing when you're tuning certain values. But I think you were talking more about features there, and that's going to be a challenge, I have to tell you. But you just look at the code of Vienna, and you will see what I'm talking about. And this is really pretty challenging. But the parameters, we have a door that is not easy to open because it's a secret door yet, right now. But very soon, the whole Eterna scripting interface is to be documented, and everyone will be able to change whatever they want.
Would that be the same case if we made, I know that there has been discussion about, making our own energy model. Would that still be the case if we did that?
The energy model, well, it all depends on what you're going to base your energy model. Essentially, when we are talking nearest neighbor, if you don't use dynamic programming, you're looking at some algorithms that have exponential complexity, or at least factorial. The only way that has been found as of today to solve the problem in polynomial time, and those are in power 4 and power, depends on which ones we are talking about. But polynomial time, you have only dynamic programming, and that was really a genius move by Zucker, I have to say.
I follow.
But otherwise, you can certainly apply other kinds of algorithms, but then you are going to run into the difficulties of, okay, how is it going to scale? And then you have exponential growth, and boom, you have something that you just can't use. So if you come up with something, which I'm not saying it's impossible, I'm just saying nobody has done it yet. Hope this answered the question.
Yeah, and I'm going to definitely look forward to being able to see what we can do with the options to designate our own parameters. I think that'll be really neat.
Certainly. That will come very soon.
All right. Thank you very much, Nando.
Thank you.